Hi, I'm Mark Hickel from Purdue University in Professor Dimitri Peroulis' research group, and today I'm going to show you a little bit about how phased array antennas work. Now, throughout this discussion, as I'm talking about electromagnetic waves, I'm going to draw some analogies between those waves and ripples in a pond using some slow motion videos I've made of water waves, because since those two types of waves obey almost exactly the same mathematical equations, we can use this as a powerful tool to visualize how electromagnetic waves work, since we can't actually see them. So, most types of antennas transmit about the same amount of power in all directions, kind of like a light bulb. If you look at a bare light bulb from any direction, it has the same brightness. And you can also see from this video, this single stream of water droplets produces a circular, uniform wave in all directions. But sometimes that's not what we want. Sometimes we want something more like a laser pointer, or an antenna that has a very narrow beam of electromagnetic waves that we can point in any direction. An example of this is in radar systems. They send out an electromagnetic wave and they listen for that wave to bounce off of an object and return to the radar. They can use this to determine the distance to the object. But if they send the same amount of electromagnetic waves in all directions, then they can't tell if they're detecting a plane coming in for landing or just an office building down the street. And that clearly defeats the purpose of the radar. So in this case, what we want instead is an antenna that has a very narrow beam of waves that it sends out so they can tell the distance to and the precise direction of the object that they're detecting. Now, contrary to what I said earlier, it's actually not difficult to design an antenna that has a narrow beam. It turns out that the bigger you make your antenna, the narrower its beam is. An example of this could be the big satellite and TV antennas that your parents had back in the day. But the problem with these is that they're big and heavy, so if you want to turn it to point it in a different direction, it's difficult to do and it's slow. So we need something better than this, and that's where phased array antennas come into play. So a phased array of antennas is essentially a group of antennas, which could be our small light bulb-like antennas, that are placed next to each other, either in a rectangular grid or in the simplest case, just in a line. Each of these antennas sends out the same signal, and we notice a very interesting result, and that is that as the sinusoidal waves that the antennas send out travel outwards, they constructively and destructively interfere with each other, so that if we've designed our array correctly, they all add together into a narrow beam in one specific direction, but they cancel each other out in all other directions. We can then look at this array as just a single composite antenna, which has a very narrow beam, which is exactly what we said that we wanted. We can also see this in this video. Here we have two streams of water droplets representing two antennas. We see that the waves they send out cause patterns of interference, forming a main beam perpendicular to the drops and canceling each other out in these other directions. We also see these other beams to the side. These are called side lobes, and although they aren't desirable, they can be suppressed in real systems, and here they're just an artifact of our somewhat limited setup. Now, in most practical systems, you'll have dozens, maybe even hundreds of antennas, which allow the beam to get narrower and narrower and more closely approximate that laser pointer-like antenna that we talked about. Now, you might wonder what we've gained, since we just traded a big antenna for a bunch of small antennas, which probably add up to the same size. Well, the answer lies in how easy it is to change the direction of the phased array antenna. So we saw before that if we send out the exact same signal from each of the antennas, that they add together to form a narrow beam that's perpendicular to the antennas. But it turns out that if we add a slight time delay to each of the signals that we send out from each antenna, that direction in which they add together into that narrow beam changes. And that new direction depends on how much time delay we add to each of the signals. And time delay is really easy to do in digital processing, which is perfect because now we have an antenna that has a narrow beam and we can steer that beam back and forth just with a little bit of digital processing, which is very fast. And we don't even have to worry about moving this big, heavy antenna back and forth. Now we can see this effect in our video. Here, if we actually change the timing of the drops a little bit so they don't hit the water at exactly the same time, then that changes the direction of that main beam. We can see here that as we change the timing, we can actually steer that beam back and forth, just like in a phased array. So that's just a really high-level overview of how phased array antennas work. I hope it helped give you an understanding and that it helped you visualize how electromagnetic waves interact with each other. Thanks for watching.